In a hostile airspace, milliseconds can mean the difference between survival and destruction. A warning tone sounds. A missile launch has been detected. The pilot deploys flares behind the aircraft to confuse the incoming threat. The missile misses its target. Well, in movies and video games about air combat, this is a common way of showing how planes can avoid missiles, right? I mean, just look at one of the most famous examples from the last few years, Top Gun Maverick. But is deploying burning magnesium particles really enough to fool an incoming missile and save the aircraft? It depends, because it's not just about the fast jets and bright flares, it's about how aircraft are detected and how those detection systems can be defeated. Why does radar lose lock when chaff is released? Why do heat-seeking missiles veer off target when burning flares are ejected? In this video, we provide a technical overview of countermeasure systems for aircraft. We will explore the science behind how modern aircraft stay one step ahead of danger, from radar deception and infrared suppression to basic decoys and advanced electronic warfare, and show the reason why in most cases the saving of an aircraft from incoming missiles is not so simple, but that a great deal of engineering is required. Before we dive right into the topic, here's an overview of what we will cover in this video. First, we will take a look at the types of threats that aircraft face in combat airspace, and the situations in which they are most likely to encounter these threats. Next, we will explore the two main categories of threat, radar-based and infrared-based. We will describe how these threats work from a physical perspective, as well as how countermeasures are designed to exploit these principles. We will start with the radar-based threats and then move on to the infrared threats. Finally, we will take a look at the next-generation defense technologies on the horizon. So let's begin by understanding the threat landscape in modern military airspace. In order to understand how aircraft protect themselves, it is first necessary to understand what they are protecting against. Modern military aircraft operate in an environment filled with layered threats. These threats differ in terms of how they detect and track targets, the types of seekers they use, and the ranges at which they engage. Let's break them down. Firstly, the threats can generally be grouped into lethal and non-lethal ones. All the tools of electronic warfare count as non-lethal threats. All kinds of missiles and other kinetic air defense systems fall into the second group of lethal threats. We will firstly explore the lethal threats before discussing electronic warfare. Lethal threats can be further subdivided by various features. In this video, we will look at grouping them by the technique they use to lock onto the target. Specifically, we will divide them into radar-guided and infrared-guided threats. Let's start by looking at threats that use radar. Radar-guided threats use electromagnetic waves to detect, lock, and guide a missile to its target. These systems include dedicated surveillance radars that scan large areas and provide detected targets to weapon carriers. One example of this is the AUX plane from NATO. Fire control radars for precise target tracking for missiles. These are built into weapon carriers such as the fighter jets like the Eurofighter. And active radar seekers built into the missile itself. We will look at this type of radar-guided threat in more detail later. All of these radar-guided systems can engage targets beyond visual range, from 20 to over 400 kilometers depending on the platform and missile type. Most radar-guided threats need to emit a radar signal in order to track their target, which makes them detectable in so-called active systems. Infrared-guided threats, on the other hand, do not need to send out any kind of signal to track their target. These threats rely on heat emission, typically from aircraft engines, to track and home in on the targets. This is known as passive targeting, which means they don't send out signals and are therefore much harder to detect. However, this passiveness also limits the range within which they can effectively detect and lock onto targets. They are therefore only used in short-range air defense tracking systems or in missile seekers for close-range guidance. This makes infrared-guided missiles especially dangerous during low-level flight, takeoff, or close combat, as they are usually effective at ranges of 2 to 15 kilometers. Before we look into non-lethal threats, we want to shortly discuss the various platforms from which these lethal threats can be fired. This helps to understand under which operational context which threat is to be expected. First, we have surface-to-air missiles, or SAMs. SAMs are deployed from ground-based launchers, often part of integrated air defense systems. Their ranges vary from short-range to long-range systems like the S-400 or Patriot system. As previously discussed, short-range systems are mostly infrared-guided and long-range systems are radar-guided. The second type of launch platforms are air-to-air missiles, or AMs. AMs are launched from enemy fighters or interceptors. They can be short-range infrared guided, like the IRIS-T or AIM-9X, or they can be long-range and radar guided, like the Meteor or the AIM-120 AMRAAM. The next type of launcher platform are naval-based launchers. Naval-based launchers, or surface warships, may use vertical launch systems to fire radar-guided missiles against airborne threats at medium to long range. The next type of launch platform are shoulder-fired weapons. Often seen in asymmetric warfare, manpads or man-portable air defense systems like the FIM-92 Stinger or the SA-18 Eagler are short-range infrared-guided systems that can be devastating at low altitude. And they are one of the main threats to helicopters in combat zones. The last type of launcher platforms are anti-aircraft artilleries. They use different kinds of sensors to lock onto an aircraft's position and predict its future path for accurate firing solutions. These systems are primarily used for short-range air defense of mobile assets. Prominent examples of this type of launch platform include the Gepard or the Sky Ranger. All of these launcher platforms are deployed together to cover various ranges and assets in modern air defense strategies. For example, the German Armed Forces defense strategy combines the short-range anti-aircraft artillery with mid-range infrared-guided IRIS-T SLMs and long-range radar-guided systems such as the Patriot and Arrow 3 to provide complete airspace coverage. However, these systems only protect the physical air defense space, not the cyberspace. For this, the second category of threats, electronic warfare systems, are used. So, in addition to kinetic missile threats, aircraft also face non-kinetic electronic warfare threats. These non-lethal threats are systems designed to disrupt, deceive, or deny the sensors and communication systems that aircraft depend on. Electronic warfare threats come in several forms. Radar jamming, which blinds or confuses an aircraft's radar. Data link interference, which disrupts communication with friendly assets or command systems. And GNSS spoofing or denial, which can degrade navigation and targeting accuracy. Some advanced electronic warfare systems, such as Russia's Krasukha or China's JY-26, can create large electronic bubbles of denial, forcing aircraft to either disengage or enter blind. While they don't destroy an aircraft directly, electronic warfare systems can render it unable to fight, navigate, or even defend itself, making them a key component of modern anti-access strategies. Together, lethal and non-lethal threats form a dense multi-domain web of danger, one that modern aircraft must detect, evade, and defeat, often within seconds. Now, with a clear picture of the threats, let's look at how radar-guided weapons work and how modern aircraft counter them. Radar-guided weapons are among the most common threats to aircraft, especially at medium to long ranges. In order to understand how to defeat them, it is necessary to understand how they work. Radar systems emit pulses of electromagnetic energy, typically in the centimeter wavelength range, anywhere from 1 to 10 GHz, depending on the radar type. When these pulses strike a target, such as an aircraft, a portion of that energy is reflected back to the radar source. It is this reflected energy that allows the radar to determine the aircraft's range, direction, speed, and altitude. The strength of the return signal depends on the radar cross-section. This is affected by the aircraft's size, shape, material, and angle of exposure. Stealth aircrafts, such as the F-22, minimize their radar cross-section using shaping and radar-absorbent materials to deflect radar energy away from the source. This fundamental principle can be employed in various ways to direct a missile towards its target. The three primary radar guidance methods are, first, semi-active radar homings. Here, the launching platform illuminates the targets with its radar and the missile homes in on the reflected energy. Second is active radar homing. Here, the missile itself carries a small radar and becomes autonomous after launch. Examples of this include the Meteor or the AIM-120 AMRAAM. And last, there are command-guided missiles. They consist of ground or airborne systems that guide the missile based on radar data, often used in long-range surface-to-air missiles. Depending on conditions and radar power, each type can lock onto the target from tens or even hundreds of kilometers away. So how do aircrafts break this lock and defend themselves against this threat, which can be beyond the line of sight. Radar countermeasures rely on the physical properties of electromagnetic waves: reflection, absorption, refraction, and interference. If you can alter what the radar sees, you can confuse, delay, or deny targeting. Let's look at how that's done. First, we have so-called radar warning receivers, or RWRs. These systems detect incoming radar signals and analyze their characteristics. They can determine the type of radar, whether it's searching, tracking, or missile guidance, and estimate the direction and potential threat level. RWRs are the first line of defense. They alert the pilot or the defensive system that the aircraft is being painted by radar. We also have electronic countermeasures. Electronic countermeasure systems actively transmit signals to interfere with the enemy radar. There are two main techniques for this. The first, noise jamming. Noise jamming overwhelms the radar with high-power interference, raising the noise floor and making it difficult to detect the target return. The second option is deception jamming. Here, the electronic countermeasure system sends false echoes, sometimes with delay or modulations, to create so-called ghost targets, which mislead the missile tracking system. These electronic countermeasure systems often use directional antennas, frequency agility, and real-time threat analysis to stay effective against modern radar systems. The last option we have is chaff. Chaff consists of strips of metallized material, typically aluminium-coated glass or plastic fibers, cut to a resonant length that reflects radar frequencies. When deployed, chaff creates a cloud of radar reflectors, each with a similar radar cross-section to the aircraft. This confuses the radar or missile seeker, which may lock onto the chaff instead of the real target. Modern aircraft can time chaff deployment precisely using cues from RWR and automated defensive suits to maximize effect. In modern combat aircraft, these systems work together as part of an integrated defensive suit, often fully automated. For example, first the RWR detects the radar log. Then the electronic countermeasures begin jamming the signal. And finally, if a missile is launched, chaff is deployed in a defensive pattern. Infrared-guided missiles track targets by detecting thermal radiation, which is the invisible heat emitted by every object. This is why infrared-guided missiles are often called heat-seeking missiles. They pose a significant threat to aircraft, particularly during low-speed, low-altitude flight or maneuvering in close combat. Let's take a closer look at how these missile seekers work. Infrared seekers detect thermal radiation, or so-called black-body radiation, which is emitted by objects, particularly the hot exhaust gases of jet engines. This radiation lies within the 3 to 5 and the 8 to 12 micron bands, known as the mid-wave and long-wave infrared regions respectively. The hotter an object is, the more infrared energy it emits. Aircraft engines, especially during afterburner use or at full thrust, are among the hottest objects in the sky. Modern infrared sensors use cooled photodetectors such as indium antimonide or mercury cadmium telluride that convert incoming infrared radiation into electric signals. There are multiple generations and types of infrared missiles. Older infrared missiles, such as the AIM-9B Sidewinder, used uncooled rear aspect seekers, meaning they could only lock onto the engine heat from behind. By contrast, modern missiles, such as the AIM-9X, IRIS-T, and R-73, use imaging infrared seekers, enabling all-aspect targeting and high off-bore side angles, as well as resistance to basic flares. These advanced seekers create a thermal image of the target, making the missile more accurate and harder to deceive. Both types of infrared missile typically have a range between 2 and 15 kilometers, but some high-end systems can reach 20 to 30 kilometers under optimal conditions. So how does defense against this threat at close range, where there is little time to react, work? As with radar-guided countermeasures, infrared countermeasures rely on modifying and faking the signal that the seeker locks onto. However, in this case, it is the thermal emission rather than the radar reflection that is modified and faked. To defeat infrared threats, we either reduce the aircraft's infrared signature or present a hotter, more attractive target to mislead the seeker. Let's look at how that's done. The first option we have are flares. Flares are the most common and recognizable infrared countermeasure. These pyrotechnic devices burn at extremely high temperatures, often over 2000 degrees Celsius, and are ejected in timed sequences behind the aircraft. The intense thermal signature generated by flares temporarily overwhelms the missile seeker, causing it to lock onto the flare instead of the aircraft. Timing is critical. Modern systems use automated dispensers triggered by Missile Approach Warning Systems, or MAWS, that calculate the optimal moment to deploy flares based on trajectory and threat angle. The second option we have are Directional Infrared Countermeasures, or DIRCMs. Although flares are effective, modern infrared seekers can distinguish between a flare and an engine plume. This is where DIRCM systems come in. These systems use high-intensity infrared lasers to dazzle or blind the missile's seeker head. Mounted in turreted pods, DIRCM systems can track incoming missiles in real time and direct a focused laser beam onto the seeker to disrupt its ability to lock onto the target. Modern DIRCM systems can also detect the type of missile and modulate their laser beam to create fake targets. This active protection system is becoming the gold standard for high-value aircraft, such as transport planes, VIP aircrafts, and helicopters. The last option we have for infrared countermeasures is infrared signature management. While not a traditional countermeasure, reducing the intensity and directionality of thermal emissions makes an aircraft more difficult to detect and track. Some aircraft are designed to reduce their infrared visibility. This can be achieved through engine placement and shielding, cool air mixing with exhaust gases, and the use of infrared suppressor on helicopter exhausts. These techniques are to infrared technology what stealth technology is to radar systems. So, how are these countermeasures deployed? Due to short ranges and high speeds of infrared missiles, these countermeasures cannot usually be deployed manually. Therefore, modern aircraft utilize automated, layered infrared defenses. A typical sequence might look like this. First, the MAWS, the Missile Approach Warning System, detects an incoming infrared missile. Then, the Countermeasure Management System classifies the threat. And finally, the system automatically releases flares, activates DIRCMs, or recommends evasive maneuvers. The split-second decision-making is the difference between survival and a successful hit. Infrared-guided missiles may be silent, but they are no less deadly. Fortunately, through thermal deception, laser jamming, and signature suppression, aircraft can survive even the most advanced infrared threats. Through this video, we have seen that protecting aircraft in modern combat airspace is a highly technical and rapidly evolving field. Whether it's facing radar-guided missiles from dozens of kilometers away or dealing with heat-seeking threats during close maneuvering, the success of a mission and the survival of its crew depend on the precise interaction between physics, engineering, and electronic warfare. However, the threat landscape is constantly changing, as are countermeasures. Looking ahead, several trends are already shaping the next generation of combat aircraft. AI-driven targeting systems. Missiles and sensors are increasingly using neural networks and machine vision to distinguish decoys from real targets. Countermeasures will need to become adaptive, capable of learning and modifying their behavior in real time. Hypersonic threats. With missile speeds exceeding Mach 5, reaction time shrinks to milliseconds. Future defense systems will need improved automated sensing, decision-making, and hard-kill interceptors, capable of responding before a human can even perceive the threat. And last we have optical and multispectral seekers. Instead of relying solely on heat or radar, next-gen seekers may use visual contrast, shape recognition, or ultraviolet and infrared fusion, requiring new types of deception, adaptive camouflage, pixel-based obscuration, and directed energy decoys. So, having looked in more detail at aircraft protection in this video, we can now answer the question from the beginning. Aircraft survivability is not just about maneuverability or speed. It's about networked, automated, and intelligent systems working together to deceive, outsmart, or outpace the threat. Although the battlefield is becoming increasingly digital and dynamic, making defense more complex and challenging, one thing will remain constant. Understanding the physics behind how threats work and how to defeat them forms the basis of every countermeasure. Thank you for joining us for this technical deep dive into aircraft protection systems.